I'm Dan Sweeney from MathSpec Incorporated. In this video, I will demonstrate how to use our Excel add-in to extract information from accurate mass fragmentation data, and I will briefly explain how this Excel add-in works. When a molecule is fragmented in a mass spectrometer, we could visualize many of the fragment ions as being composed of smaller imaginary subfragments. A subfragment could be considered a block of atoms that hold together during the fragmentation process. First, we need to find possible masses of these subfragments. Possible subfragment masses can be obtained by addition and subtraction. The three types of subfragment masses are neutralized fragment ions, simple differences between fragment ions, and some mass differences. The next step is to then check combinations of these possible subfragment masses for partitions. The accurate masses here have been multiplied by 10,000 to convert the 4 decimal place rational numbers into integers. The Excel add-in checks for sets of 3, 4, or 5 masses that sum up to the accurate mass of the whole molecule. These are partitions of the analyte's accurate mass. This operation is CPU intensive, and it would be very difficult to do without using a computer. Scoring is based on how many individual fragment ions can be accounted for with various combinations of these subfragment masses and how intense those fragment ions are. Possible molecular formulas of the whole analyte are obtained based on the isotope pattern and the accurate mass of the precursor ion. The subfragment masses that comprise mathematical partitions are then converted into combinations of atoms in such a way that all atoms that comprise a proposed molecular formula of the whole molecule are allocated into subsets of 3, 4, or 5 groups of atoms. This is a partition of the set of all atoms of a given formula into multiple subsets. Subsets are mutually exclusive. Each atom of a proposed molecular formula can be found in one and only one subset. This subset is what we call a subformula. Possible spatial alignments are then assigned based on logic tables. From the alignment, we can picture the analyte as a modular structure. Let's demonstrate the Excel add-in using some methionine data as a simple example. The Excel add-in requires at least one accurate mass fragmentation spectrum, here called an MS2 spectrum, and the isotope pattern of the precursor ion from a full scan MS1 spectrum. Multiple MS2 spectra obtained at different collision energies can be combined. This is a very simple example, but it will illustrate the major features of the Excel add-in. Let's start a new Excel workbook. Clicking on Add-ins brings up 2 icons on the left side. The icon on the right launches the worksheets that are needed for the mass spectral analysis. The data input worksheet is initially the active worksheet. I should point out that whenever the add-in first launches, a help worksheet is temporarily available. I'm going to save this workbook as methionine data. The MS2 data is pasted into columns A and B. When we're using 2 or more MS2 files, as in this case, I generally use relative intensities rather than absolute intensities in column B. The isotope data is pasted into column F. The masses in column E are not needed. In column C are 3 checkboxes. For this demo, I will use all default settings. The default settings for the checkboxes are positive ion mode, even electron fragmentation, and no requirements for all fragment ion formulas being subsets of the molecular formula. Consistent formula is checked when there is a high confidence that there are no extraneous fragment ions in the data. Farther down in column E, rows 12 to 20 are element maxima. The Excel add-in only supports these 9 elements. For setting the maxima, if for example you're confident there's no sulfur in your sample, setting the maximum number of sulfur atoms at 0 might reduce the total number of potential formulas and the computation time. In this demo, I will leave all the maxima blank. Any number of atoms will work. Further down are 3 list boxes. The top one is for selecting the error window. The default window is 3 millidaltons. The expectation is that all formulas and subformulas accurate masses will differ from their exact masses by less than this error window. This window is also needed to combine the MS2 spectra at the 2 collision energies. The isotope ratio error is an absolute error. No matter what units were used for recording intensity, the values will be converted internally into a scale of 0 to 100% before applying this window. The formula restriction setting of 4 is relatively high to compensate for having no limits on the number of fluorine atoms. A higher restriction value filters out some less common formulas. To start the analysis, I need to click on the Transform button. This flag is a warning that the neutral loss of 48 Daltons might be a combined loss of hydrogen fluoride and carbon monoxide, but the individual losses are not seen. If this were the case, then the collision energy used might have been excessive. The active worksheet is now partition 1. Let me move this up to get things in view. Each partition is a different view of the data. The Excel add-in has combined the 2 MS2 spectra and did not duplicate any fragment masses. For this partition of 4 subformulas, the Excel add-in did not assign any combination of these subformulas to the 60.0035. When there are many fragment ions, only the most intense fragment ions and smallest neutral losses are used for partitioning. The partition score, here 80, is based on how many ions are assigned and their relative intensities. The isotope ratio, calculated from the MS1 data, is shown in italics. The isotope ratio below that was estimated from the proposed formula of the analyte. The average subfragment error is the difference between the subfragment masses calculated from the data and shown in row 23 versus the exact masses of the subformulas in row 37. The relative feasibility takes into account both the average subfragment mass error and how probable each subformula is likely to be found. The proposed molecular formulas are hyperlinked to Pubchem compound. So there are 1,079 compounds that have the formula C5H11NO2S. The Excel add-in will find up to 6 partitions. The partition scores will drop as we go from partition 1 to partition 6. Partition 2 has 2 formulas because it has 2 different subformulas for subfragment number 3. and that leads to two different molecular formulas. Each formula has a different isotope ratio, mass error, and feasibility score. At partition 6, the score is now down to 43. We can compare all 6 partitions in the summary worksheet. The mass error scores are the same for each row of each partition. To compare the mass errors, I can pick out the formula of the precursor ion in each one and then sort by mass error, smallest to largest. In this case, we can see that the formula C5H11NO2S is giving much lower mass errors than the formula C5H8NO3. I can copy a molecular formula and paste it into the isotopes worksheet. It's positive ion data. Let's use the default 50K resolution. The two tables at the top now have the exact masses of the isoptomers of the first and second set of isotopes for that formula. The bottom graphs are color-coded displays of those regions for comparison to the unknown analyte. It would be hard to miss the sulfur 34, and the presence of a sulfur 34 in the experimental data would completely rule out that second molecular formula of C5H8FNO3, which has no sulfur. So let's go back to partition 1. Here we talk about the alignment of subfragments. In this case, there's only one alignment possible with these assignments, and that's all connected to white subfragment. We can visualize this analyte as a 4-unit modular structure where there's a 3-carbon subformula at the center to which the other 3 subformulas are directly attached. If we compare this modular structure to the molecular structure of methionine, it appears to be a very convincing match. However, mass spectrometry can only show us combinations of atoms. Essentially, a subformula is just a block of atoms. For example, the 3 subformulas on the outside of this modular structure are all connected to a 3-carbon block in the center. But to which of the 3 carbons? We cannot tell that from the data. Is the CH2O2 subformula block attached to the center by a carbon or by an oxygen? We cannot tell that from the data. For most analytes, one or more modular structures is as far as we can go with mass spectral data. The final structure proposal now depends on background information. Background information is very important. If the analyte is likely to be a commonly used compound or related to a commonly used compound, we can also search the Pubchem compound database of about 114 million compounds. It is possible to search the Pubchem database for substructures. Many smaller subformulas generated using the Excel add-in correspond to only a few substructures, but these substructures are usually very common in this large database. For example, searching the entire Pubchem compound database for compounds having the substructure corresponding to a methoxy group will either just stop after a million hits or time out. To make substructure searching more practicable, scientists at the National Center for Biotechnology Information recently developed fast substructure searching, which limits the Pubchem search space to a single molecular formula. Fast substructure searching has now been incorporated into our Excel add-in as a new worksheet called Search Within. About 120 small subformulas have been designated in SMART's substructure notation and stored in the Excel add-in. Let's copy row 37 of partition 1 and copy this. We'll go to Search Within. The figure here is a reminder to use paste and transpose to get the row into a column. We want to use this paste. Now we need to copy the molecular formula and paste it into cell B1. It's a little tricky to copy a hyperlink, so I'm using the space up here. So this is the formula that we want to search for these subformulas. The example row 2, we want to do search within. Search within B1. Now the hyperlink function doesn't follow the hyperlink, it just generates it. Clicking on that hyperlink will generate a listing of all compounds in Pubchem having that formula. The listing is called a text catch key, and it will be saved for several hours in Pubchem. So I want to copy this. I don't want the quotes. And I'll paste it into B3. Now we cannot use the subformulas like those in column D to search the Pubchem database directly. The substructure searching here uses SMART's notation. The Excel add-in must first convert subformulas into that format. Only small subformulas can be related to substructures and converted into SMART's notation. For example, the CH4S subformula implies an analyte that has a thiomethyl substructure but not a methyl sulfone or a methyl sulfoxide substructure. I'm going to click on add-ins again, and this will bring up again those two icons, but this time I'm going to click on the icon on the left side. The icon on the left side will convert the subformulas into SMART's notation. In cell B4, when more than one of the subformulas have SMART's notations, then the SMART's notations are combined, each one separated by a period punctuation mark. So for example, this is the center C3H2, and there's periods on both sides of that. The periods mean that the corresponding substructures are mutually exclusive. The individual SMART's notations for each subformula are generated in column E. If the text string in B4 is longer than 145 characters, this would require a separate search of each SMART string. Examples of compounds that have some common subformulas can be seen by using hyperlink examples. D1, and I can fill down, and for example, if we click on these are the hyperlinks, and if we click on that one we will get some examples. Screen is a little small, but these are some examples of compounds that have a CH2O2. To now do the substructure search, I need to type in, you have to go back over here, and in B5 I need to type in generate another hyperlink. Smarts. And here I say B4. Okay, so this makes the hyperlink. The maximum length of this smart string is 140, about 145, so we're at 125. So now to follow this hyperlink, I just click on this. So now it's searching the 1,079 compounds. So this generates a list of all the compounds that had that formula C5H11NO2S, and also had the 4 substructures that we were searching for. I'm going to copy those. A lot of it's off the screen. And go back into Pubchem, and I'll paste these in. And we want to, again, we want to look in the compounds database. So we have 125 results. Now it's a little hard to see, but there's a button over here that says push to Entrées. And here we can look at up to 200 compounds at a time. Looking these compounds over, methionine is a metabolite of great interest, and so many of these 125 compounds, although they all have the formula C5H11NO2S, many of them are isotopically labeled. We can remove these compounds by screening for exact molecular mass. So I'm going to go back to partition 1. So this is the accurate mass of the analyte that we measured based on the fragments. I'm going to copy that. And now I can go back into Pubchem, go to Advanced Home, Chemical Search. I'm going to paste that in and put a colon, paste it one more time, and then we want to use MMAS for the monomolecular exact mass. So we're going to look for compounds in this range. I'm going to subtract 3 millidaltons here, and I'll add 3 millidaltons here. I want to find all the compounds in Pubchem in this mass range. We have to use Entrées to do this exact mass search. We now have 2,457 compounds with that exact mass within 3 millidaltons of our analyte. If we go to Advanced, this brings up the search builder in Pubchem. What we want to do is we want to find the intersection between these 2,458 compounds that had the exact mass that was within 3 millidaltons of our measured analyte mass, and the 125 compounds that had the formula we wanted and the also the substructures we were looking for. So I'm going to add both of these in to the builder, and what we want to, you could say or, but the compounds that we're looking for have to be in both sets. So we're looking at the intersection of these two sets. So we want to say and. We'll search that. So now we have 42 compounds, and these all have the right mass, and they have the right subfragments and the right formula. We can further screen these compounds and eliminate all compounds that have an unlikely alignment. The first compound in the listing has each of the three outside subformulas attached to a different carbon of the C3H2 subformula. This compound would be consistent with the mass spectral data, so I can check that off. The next compound, the C3H2 piece that ought to be holding everything together, is on the outside, so this one won't work. Number 3 will work. It's a C12, I believe, isotope. Number 4 is not going to work. The one subfragment is not connected to the rest. So we can go through these. Number 6, that should work. Number 7, this is interesting. It has the oxygen of the CH2O2 is connected to the C3 instead of the carbon as we had in some of the others. So we can go through this and we'll find at the end there's about 26 compounds that are consistent with this mass spectral data. And we'd expect that many of these compounds would also behave chromatographically like methionine. The Excel add-in demonstrates the uncertainty in mass spectral data even for a simple compound like methionine. However, combining the analysis of mass spectral data with background information about the analyte's history is usually sufficient to tentatively identify a compound. And this slide is a brief summary of functions and hyperlinks that are found in our Excel add-in. I want to thank you for watching this video, and I hope that you will try this approach with your data.